So we'll be recording this lecture and also live streaming it on YouTube.
Okay.
This Zoom meeting is basically exclusive to the club members only, and for rest of the general audience, we'll live stream on YouTube. So are you okay with that?
Yeah, that's fine. Yeah.
Okay, sure. Thank you so much, sir. Okay, sir. You can wait. I'll give you the streaming. Yes, sir.
All right. So I'll get started. Thank you for your kind invitation. I will be speaking about gravitational lensing. It's a subject which in theory is centuries old, although observationally it is just about a century old. So we'll go through historical developments. Okay. All right. So the first analysis of bending of light by gravity was done by Soldner, and this was done more than 200 years ago. And at that stage, he used Newton's laws, Newtonian gravity, and he made use of the fact that the mass of the particle which is moving drops out of the equation thanks to the equivalence principle. Of course, people didn't know about equivalence principle as clearly then, apart from Galileo's formulation. So once you plug that in and you do the calculation, the equation as it is looks a little bit horrible. But what you can do is you can switch variables. You can switch to a variable 1 by u. And instead of writing down a vector equation, you can write down an equation for the distance between the attractor and the photon. In this case, he was interested in the Earth. He found that the deflection angle is 2gm by bc square, where b is the distance of closest approach or impact parameter. Both happen to be pretty much the same in this case. And for the Earth, he found that the angle simply cannot be measured. Then he asked about the Sun, and that calculation gave him an angle of a little bit less than 1 arc second, 0.84 arc seconds to be precise. And of course, he realized that you cannot see things close to the Sun, but he published his result and he let it be. There was not much of a follow-up because soon after this, the corpuscular theory of light went out of fashion and people drifted towards wave optics. And of course, it was known that it was not known how waves would respond to gravitational force. So it remained till Einstein came along, and what Einstein did was to apply the equivalence principle, which is something similar to what Soldner did. But Einstein's hope was to essentially connect it up with special relativity, because by this time people knew the speed of light a little bit better. And of course, Einstein had shown in his special theory of relativity that using speed of light as the ultimate speed, as the limiting speed, gives rise to interesting phenomena in space-time. So just to recap, in equivalence principle, one thinks of equivalence between two sets of frames. One is on in a uniform gravitational field, and the other is in a uniformly accelerating frame, which is away from all gravitating masses. So it could be in a rocket far, far away. And what Einstein said was that it is not possible to do any experiment within a small room in both these situations, which will let you figure out which of these two frames you are in. And therefore, any experiment that you do in one should be, it should be possible to replicate that in the other frame. So on basis of that, he said that, look, if I am in a rocket and a beam of light enters from the side, because the rocket is moving and accelerating, the light beam will not move in a straight line. According to me, it should move in a curved parabolic path. And therefore, the same thing should happen if the frame is that of uniform gravitational force. And he arrived at the same equation and the same numbers that Solner did. And Einstein started writing to astronomers and visiting observatories, trying to persuade them to try and make this measurement. In 1912, there was an Argentinian expedition to Brazil. They were not really planning on making this measurement, but they got to know from other people that such a thing could be of interest. Unfortunately, that entire expedition was washed out. Einstein also tried to persuade observatory directors to look at pictures taken during earlier solar eclipses to see if some measurement can be made. Nothing seemed feasible. The next solar eclipse, total solar eclipse, was to be visible in Europe, in Crimea, going up to Sweden, but not really visible in the Western Europe, Germany, France, etc. So a lot of expeditions were set up to go to Crimea. There was one or two to Sweden. Unfortunately, by the time the eclipse was to happen, First World War had started, and all of these expeditions got caught up. All the people who had come from England or France or America, their equipment was confiscated and put in cold storage, and they were sent back. And astronomers who had come from Germany, for example, there was one astronomer whose name will come up later. He was arrested, and Einstein had to use his influence to get him exchanged get him out in a exchange of prisoners of war. So Einstein, in the meanwhile, had been working on completing the general theory of relativity, which he did in 1915. And when he revisited the calculation, he found that the answer in his new theory is not 2gm by bc square, but 4gm by bc square. So it doubles in telling people that they should try to observe it. Of course, war was going on, meaning that he could not directly communicate with anyone outside the German system. And situation was such, because of his pacifist views, that within Germany he did not have a whole lot of support. It was only through some neutral countries like Netherlands that the details of his calculations and his appeal to make these observations leaked out. This was picked up by Eddington in Cambridge. Now, Eddington was one of few astronomers who had the mathematical training to be able to learn and reproduce calculations in general theory of relativity. And at the same time, he had the training of an observer who could make extremely fine measurements. He had, in fact, been involved along with Dyson, who was the Royal Astronomer in England at that time, on for making observations of distances to stars by observing parallax. And Dyson had devised a method for making these measurements, which Eddington had refined further, and both of them were quite good at using this. So they realized between the two of them that forthcoming eclipse in 1919, in fact, May 29, 1919, would be an excellent opportunity for two reasons. One is that the duration of uh, of the eclipse was one of the longest. It was going to be almost 6 minutes long. And the second reason why it was special was that the sun was going to be in the constellation of Taurus, very, very close to the Hyades open cluster, meaning that there are several stars, a number of reasonably bright stars, which could be used for any observations. So three different sets of observations were made, two in Sobral in Brazil and one in Principe. I'll give a little bit more story of these expeditions. So all of the expeditions were planned while the war was on, and the plans were executed just at the end of the war. In fact, they had to take help from US Navy for even getting hold of a carpenter for fitting some things, because they wanted to be ready and not rely on any local innovations for setting things up. Sobral, Brazil, the team took two telescopes because one of the members, so England had something called a permanent joint eclipse committee between the Royal Society and the Royal Astronomical Society. And it had gentlemen astronomers who were not professionals, and it also had professional astronomers combining their efforts. So Father Corti was one of the senior amateur observers, and he had made some observations of the 1914 eclipse from Sweden, and he recommended that apart from the bigger telescope, which was taken to Sobral, that a smaller telescope also be taken, because his own experience with the smaller telescope had been much better than with the bigger telescope in 1914. Eddington went to Principe mainly as a part of a deal where his pacifist views had gotten him into trouble, and he would have gone to jail for not participating in the First World War. But the Army and Navy were persuaded that an expedition to Principe is equally bad, and therefore let him do that job instead of serving in the war. So these observations were carried out. The smaller telescope in Sobral was the best performer of the three. Principe had a lot of clouds, so they could not get adequate number of observations. The bigger telescope performed badly in Sobral, and the reason appears to be a sudden change in temperature. I'll show you a picture of these things. So there are two telescopes here. This is a picture from Sobral. The telescopes were fixed horizontally, and moving mirrors were fixed in front of them. This is called a coilostat. And an arrangement of falling weights was made so that the sun could be tracked for a period of 20 minutes non-stop. The bigger telescope suffered from a sudden change in focal length due to the change in temperature. This was not appreciated or fully understood at that time, whereas the smaller telescope did not suffer from a similar fate. You will notice that the smaller telescope is mounted in a strange way, and this was done in order to maximize the number of bright stars from the Hyades cluster, which could be observed in the same frame as the sun. So this thing was actually set up on the outskirts of a race course in Sobral. Principe is a small island, and when Eddington and his partner landed up in Principe, saying that they were told that sky would be clear in May, people laughed at them, saying that May is the worst month in terms of cloud cover. There was one other possible location on the West African coast. However, that had been discounted because they were told that the weather there is likely to be bad. Unfortunately, weather at that spot was, fortunately or unfortunately, it was almost perfect, but the expedition of biologists sitting over there did not have any instrument to make any observations. So the full details of the expedition, the observations, calculations, and results were published in this paper in 1920, written by Dyson, who was the astronomer royal at that time, Eddington, who was by this time director of Cambridge Observatory, and Davidson, who was an assistant. So as you can see from contents, it gives goes to great length to discuss the purpose of the expedition, preparation of the expeditions, the individual expeditions as to what happened over there, and then it goes on to do calculations and present results. So those of you who are interested in the history of astronomy should definitely look this up. It's a wonderful paper to read. So this is the summary from this paper. On the x-axis is distance from the edge of the sun. Notice that the scale is inverted. So things which are on the right are actually closer to the sun, and things which are on the left are further away. On the y-axis is the radial displacement between the location of the star at the time of eclipse as compared to its location normally when the region is far away from the sun. So in order to do this comparison, reference plates were taken. The group in Sobral actually waited for 2 months and took comparison plates from the same location. It was not possible to do that from Principe because the shipping company which ran ships from Portugal to Principe was about to go on strike. So Eddington essentially left as soon as he could, but he made arrangements for a third use of a second field for setting up comparison plates from Oxford. So results from main telescope at Sobral, if they assumed that the scale of the image had shifted, were consistent with Newton's predictions. But if they assumed that it was just off focus, then they were consistent with Einstein's prediction. But because they could not figure out exactly what had happened, the astronomers decided to essentially leave those results out. The results from smaller telescope at Sobral were the main drivers for this particular plot, and results from Principe were consistent with it. Now the dots over here, the filled black circles, are data points. The dashed line is prediction from Solner or from equivalence principle. The thick line is the thick black line, which is the diagonal, is the prediction from Einstein's theory, the general theory of relativity. And the thin black line is the best fit to data. So it is actually close to, but slightly higher deflection than suggested by general theory of relativity. Much better results were obtained by American astronomers led by Campbell for the 1922 eclipse in Australia. And he, in fact, did an extremely good job of trying to fit everything very, very well. It's worth reading about his preparation and his expedition because that particular eclipse was visible from a coastal region which did not have any easy connection for travel, which means everything, the entire equipment had to be transported in small boats. So Campbell essentially had to go and stay there for a longish period, setting everything up. But there was a little bit of an ego involved because Campbell had asked one of his assistants to observe an eclipse in 1917. The assistant was Curtis, who went on to become a famous astronomer in his own right, but he worked more on galaxies than on stars. And his analysis of the 1917 eclipse had to be retracted at the last moment because Eddington, etc., told Campbell that what they are getting from the 1919 eclipse is very, very different. So Campbell tried to outdo Eddington, etc., in terms of accuracy, and he did a much better job. So these are the constraints now, and you can see that the error bars from optical measurements are still very large. These are in the left panel, whereas observations from radio shown in PLBI and other measurements are much, much better. So, but the summary is that Einstein's theory passes the test with flying colors, with much reduced error bars now, as compared to all other competing theories of gravity. And to show you how much we have progressed, this is a paper written by an amateur astronomer. You can see his picture with his equipment in the middle panel, which he wrote based on measurements of the August 2017 total solar eclipse. And this was done using amateur equipment, a CCD camera, which he had set up, and a small telescope. And on bottom right, you can see his plot, which is analog of the earlier plot which I showed you. Oops. Sorry. Yeah, so you can see the reflection angle decreasing as we go further and further away from the sun. So going back to coming now to mainstream gravitational lensing, what Eddington observed was deflection around the sun. He tried very hard to make observations around of lensing by other stars, but he was not successful. In 1937, Zwicky, a Swiss astronomer, he suggested that galaxies and clusters of galaxies may be able to cause detectable gravitational lensing, because his estimate of the mass of clusters of galaxies was much, much higher than what seemed to be the case if you just added up masses of all the galaxies. And the numbers were kind of off by a factor of 100. First observations of multiple images of a quasar were observed in 1979. So going away from the solar system, this was the first set of observations of gravitational lensing of an extragalactic object. So the way gravitational lensing works is that we have a source which is probably very, very far away. We have an observer either at the Earth or in orbit around the Earth. The light from the source is bent by some intermediate concentration of mass, and as a result, we end up seeing the same object in different directions in the sky. Of course, all the angles here are highly exaggerated because things like deflection angles are typically in arc seconds. But nevertheless, one can see multiple images of the same background source. And since the amount of deflection depends only on the mass interior to the light rays and also on the distance from the center, so as you recall, it is 4gm by bc square. Therefore, one can make an estimate of the amount of mass enclosed using gravitational lensing. Further, because the reflection angle is fixed, the amount of deflection which we observe, or the separation between images that we observe, is maximum if the lens is roughly halfway between the source and the observer. So this can be written down as a nice mapping, except in the mapping, the arrows are now reversed. We shoot rays into the lens plane or the image plane, and then we deflect them onto the source plane. So I have a mapping from the image plane to the source plane, and this mapping, because each ray is deflected precisely once, and one can show that the deflection is proportional to the gravitational potential of the deflector. So since it is just a one-time deflection, it can be written as a one-step map between the image plane and the lens plane, described by a potential. So if I have a circularly symmetric lens, then I need to have enough mass in the lens to be able to cause multiple observed images for a single source. Okay, so in this case, I have on the y-axis, I have the observed angle. On the x-axis is the actual angle between, let us say, the line joining us and the center of the lens projected to the source. So as we move the source on this line, okay, it appears at multiple places in the observed plane. So there are places, so let's say over here, if I draw a horizontal line, I will see it at 3 different places and I get multiple images. So one can think of the most symmetric situation where the source, the lens, and the observer are in a line. In this case, of course, there is an axial symmetry, and instead of seeing images, discrete images of the source, we will see a ring. And one can write down an equation for the angle which describes the radius of this ring on the sky. This is called an Einstein ring. And here is an example of an almost perfect Einstein ring. This is lensing done by a luminous red galaxy of a background star-forming galaxies, they're much higher energy. Now, since one can describe this gravitational lensing as a map between the image plane and the source plane, and as I said, the deflection is proportional to the gravitational potential, one can show that all characteristics of the lens can be worked out from the lens potential. And in this entire map, so I talked about shooting rays in the image plane and then deflecting them onto the source plane. Now, what happens if I have a bunch of rays in the image plane which land up at the same place in the source plane? In that case, an area element in the image plane would have mapped onto a point in the source plane, and that would be a singularity. And nominally, at such a point, the magnification is infinite. So all locations on the image plane where the magnification is infinite for a given source redshift, they are called critical curves, and this corresponds to the Jacobian transformation from the image plane to the source plane vanishing. And these are just contour levels of eigenvalues of the second derivative of the potential. Okay? And these are smooth curves. But if I take a critical curve in the image plane and I map it into the source plane, this forms what are called caustics, and caustics need not be smooth and can have cusps. Okay, and cusps form. Let me not go into this particular detail. So this is an example for an elliptical lens. On the left side, you see the image plane and you see the critical curves. Because I'm dealing with a two-dimensional system, so the image plane and the source plane are two-dimensional. But I have to take derivative of the potential along two different directions. So the second derivative of the potential will be a second-rank tensor or a second-rank matrix, and it will have two independent eigenvalues. So when I say critical curves correspond to contours of eigenvalues, I will have actually two sets of curves. So the thick black line corresponds to the eigenvalue, to the larger eigenvalue, and the thin black line to the smaller eigenvalue. Historical reason, the images corresponding to the higher eigenvalue are called tangential, and the ones correspond to the smaller one are called radial. Now this is drawn for a particular source redshift. If I draw it for a different redshift, I will still retain this kind of mirror symmetry about two lines, which are shown over here. And it turns out that any point of the critical curve on these lines will map to a cusp. Cusp is a pointy thing which you see over here or over here. Okay. So in an elliptical lens, I can draw a cross and the caustics will only be found at these particular points. And this caustic is to be seen in the source plane. So this is not new. This is something which has been known for any number of years. And caustics for an elliptical lens as a function of distance were first analyzed back in 1986 by Ramesh Narayan and Roger Blanford. They used generalized Fermat's principle from optics to gravitational lensing. And what is shown over here is for an elliptical lens, the caustics are drawn for a whole set of source redshifts. So what we have done is to simplify this description, you can see that the cusps in the caustics are always along across, and that is already figured out over here, displayed over here in this simple curve. So what we have done recently is to work with some characteristics of the eigenvalues and eigenvectors, which provide a simpler map of the gravitational lens. So let's see what happens in gravitational lensing. If I take a source galaxy, and in the simulation, of course, I can move it in the background. You see multiple images forming. In the first round, you just see it as it is, and then we will run it again. So first thing you notice is that when the galaxy is far away from the lens, there is only one image. When galaxy is close to the lens, there are multiple images. So the galaxy has to be touching or inside the caustic for multiple images to have form. Second thing to note is that when the source galaxy crosses a caustic, at that stage, a pair of images is formed around the corresponding critical curves, or a pair of images is annihilated at the corresponding critical curves. So I will show that again and watch it carefully. So it's going to touch the green caustic first. So I should form images around the green critical curve here. Then it is going for the red one, and I'm going to form a pair here. And when it is inside, I have this nice cross which builds up. Now it is going out of the red one, so I should have an annihilation over here. And now it will go out of the green one, and I have annihilation over here. When it forms a cross, they are actually lined up in a largish ring, which has a radius of curvature which is of comparable size to the lens itself. Okay, so let's run it once again. So you see this ring-like structure which forms is very big, and it is almost the same size as the cluster on the sky as seen from these critical curves. Now, our recent work has been on identifying some special points where very interesting image formations happen. So now you will see that the galaxy will touch this double cusp over here. And I will form two pairs of images up there. So it comes and goes because these special point caustics are not as stable as line caustics which are there. So this particular type of caustic which forms, image which forms, is called a hyperbolic umbilic. I will just run it again. It is a degenerate point, which is why the critical curves for the radial and the tangential arcs are touching each other. So we'll have formation of 4 images here in a ring, but 2 features. The ring is not centered at the lens, and the radius of the ring is much, much smaller than the size of the lens. Here. So this kind of a point was known earlier. It's not something new which we have devised. If I go back to the image from Narayan and Blandford, you can see in the third frame 2 points which are marked as U. So they were aware of the umbilic, but because of its transitory nature, they did not pay much attention to it at that time. Though I am aware that Roger Blandford has been going around telling people to look at such points more carefully as more data was coming along. So one last look, and then we'll move forward to other types of images. So it turns out that the classification of these point singularities is something which is done on the basis of catastrophe theory. So it's a theory which deals with classification of singularities of mappings. And one very important theorem in this was proven by Thom almost 100 years ago, where he said that the precise nature of the map is important, but there are some aspects which are dependent only on what he called as a codimension. And the codimension is that if I have a singular mapping, in this case, we are dealing in 2-dimension to 2-dimension, there are only two ways, two classes which you can have. You can have a 2-dimension to 1-dimension map, so an area element mapping to a line, or you can have an area element mapping to a point. So he said that an area element mapping to a point will have a distinct class of singularities, and they can all be classified. And similarly, area to a line also is a class which can be enumerated and written about. What is more interesting is that if one was to have a similar mapping in, let us say, 3 dimensions, then all the singularities from 2 dimensions to 0 would replicate in 3 to 1. Okay. So the codimension is the number of dimensions in which your mapping is singular. So based on that, the number of codimension 2 singularities in gravitational lensing is precisely 3. There are 2 types of umbilics and one other type of point. So this hyperbolic umbilic has been seen, as was pointed out by an astronomer, de Zivry, about 10 years ago. So this is picture of Abel 1703. There are many arc lensed galaxies over here, but there is one in the middle which appears to be the umbilic. Now notice that the one which is marked as umbilic is not near the center of the cluster. It is slightly offset. So I'll close up on this. So this is a 4-image system, which is probably an umbilic. The astronomer who identified this as an umbilic proposed that this is probably the only umbilic which will ever be seen in the sky. And this is where we disagree, because our calculations suggest that it should be seen more regularly as deeper observations become more and more common. So this is another kind of umbilic called elliptic umbilic, where you have not 4, but 6 images forming. And the image formation is very, very peculiar. So it forms a Y-shaped structure. This, as far as we know, has never been seen. And our analysis suggests that this is going to be an extremely rare type. And if we see one, we will be very, very happy. This is also called as a pyramid. It's another approach towards a pyramid. So we've seen a couple of instances where some kind of an outward bent arc is seen, like we see over here, as the source is coming out from the inner triangular cusp, and you see a boomerang shaped image over here. I'll show it once again. But we have not been able to ascertain for sure whether it is a pyramid or. Now, so you see this outward bent boomerang shaped image form. There are other types of singularities. So this is the third and the last one, which is called a swallowtail, in which you get an arc. So focus on C3, which is the one at the bottom, and you get a arc which is kind of straightish. And unlike the umbilic, the hyperbolic umbilic, where I showed you that the ring which forms has a very small radius as compared to radius of the cluster. Over here, the radius of curvature is much, much bigger than the radius of the cluster. So this has been two examples of this have been seen so far. So this is in Abel 370. So you see lots of curvy lines here. Many of them are bogus because these are images of asteroids, because this exposure is taken over many, many days. So these S-shaped curves are all pictures of asteroids in the field. Swallowtail is here at the bottom. Okay, straightish arc, which is seen over here. So gravitational lensing has been used for many purposes. Probing dark matter in clusters is one, but the most spectacular achievement was to look at dark matter in a colliding cluster called the bullet cluster, where the galaxies of belonging to the two clusters have gone through each other. The gas is stuck in the middle. So one sees hot gas shown in pink over here in the middle. But the mass the dark matter mass has gone along with the galaxies, which is marked in blue. And that reconstruction is done using lensing. And of course, we know that gravitational lensing has been tested in the extreme strong gravity regime as well. This is from the Event Horizon Telescope, where we see this ring-like image because any unbound orbit cannot come closer than about 1.5 times the Schwarzschild radius of a black hole. So as you try to bring the photon trajectory closer, it bends more. It begins to loop around once, twice, thrice. But if it goes closer than 1.5 times the Schwarzschild radius, then it just falls into the black hole, which means for a distant observer, you will essentially see a hole in the middle. Appears to be brighter on one side because of beaming effects which come from special relativity. So essentially, with gravitational lensing, it has been used in weak lensing, strong lensing, as well as extreme lensing regime. In our own work, what we have done is to demonstrate that by analyzing mass maps of many clusters, that the point singularities which we are talking about, like the umbilic and the swallowtail, are fairly common. It's just that we need slightly more sensitivity than is normally available at present. So therefore, the next generation of deep observations with the James Webb Space Telescope, which is going to be launched in a year or so, are likely to get us a large number of such images. So I'll just leave you with a summary. So gravitational lensing in the weak limit is described by Einstein's theory of relativity, and observations of lensing in the strong gravity case are also consistent with Einstein's theory, as we have seen in images from the Event Horizon Telescope. Lensing by galaxies and clusters can be described in terms of a lens equation, and characteristic image formations can be described in terms of singularities of this map. So what we have done recently, this is with the student Ashish Meena, is we have developed and implemented algorithms for finding all singularities of any given lens map. And this is a very compact representation of the lens map. All the other representations are far more cumbersome. And we expect that this will be useful in the coming decade, as the number of known lens systems is expected to increase by several orders of magnitude. And the main quantitative prediction which we have made is that, unlike the earlier prediction that we'll see only one oblique in the sky, and that has been seen, we feel that at least 1 point singularity of either umbilic or swallowtail should be seen for every 5 lensing clusters when the deep observations are made by the James Webb Space Telescope. I'll stop here. Thank you. We can take questions.
Guys, feel free to ask questions now.
Sir?
Yeah.
First of all, thank you for that amazing lecture. I had a few doubts when you were talking about two-dimensional mapping, and when you're trying to extrapolate it to third dimension, the single, like the 0 points become 1. That part.
Yeah, so that is from catastrophe theory, which says that in any given map, if I have a map in, let us say, n dimensions, n is not important. If I have a singularity of a type where I go where I have reduced the dimension from n to m, then n minus m is the important number in classification.
Right. So, so can we predict maps of higher dimensional through lensing? Can we predict?
We can accept that lensing is structured to be a 2D map, so we don't know what the 3D analog would mean.
Right, right. Thank you.
But there are other instances where we have mappings which are valid in 1 dimension, 2 dimensions, 3 dimensions, and even more. And over there, this becomes extremely important in the sense that I do not have to reinvent the wheel. If I go from 2 dimensions to 3 dimensions, then 3 to 2 and 3 to 1 will essentially get picked up from what I knew in 2 dimensions. It is only 3 to 0 which will be new.
Oh, okay. Thank you, sir.
So I had a question.
Go ahead.
Yeah,
okay.
Go ahead.
So galaxies are constantly rotating and changing their position. So how do we take consistent measurements in a long term? How do we properly compare? If like the design of our lens changes, then how can we be so sure about positions of a star and match them over time?
Right. So one has to look at the time scale over which something will change. For example, in our own galaxy, if I am looking at lensing by a galaxy, then things will change over a time scale of a few million years. So that time scale is not very important. But what can happen is that within the galaxy, there are stars which are moving around, and one particular star comes into a location where it can suddenly give me a boost in lensing. So that gives me time variation, and for that one can make statistical prediction, and that those predictions have been tested against observations. Within our own galaxy, for example, we searched for possible existence of compact dark matter within the halo of our own galaxy by looking at monitoring the brightness of stars in satellite galaxies, which this large Magellanic Cloud and the small Magellanic Cloud. So to do this in late 1980s, early 1990s, astronomers set up a system to monitor brightness of more than 1 billion stars on a weekly basis. Because over there, the expectation was that because of some star or a compact object coming in between, the brightness of the background star will change over a time period of 10 to 20 days. Okay. So there were two projects, Ogle and Macho, and between the two of them, they were monitoring each one of these million stars at least once in 2 days, if not more frequently. Okay, so time variation can be important, but one has to understand what are the timescales involved. And if we are looking at lensing by a cluster of galaxies, in that case, the timescale for variation would typically be hundreds of millions of years. So we don't really worry about time, change with time. But we do know that if one of the galaxies in the cluster is close to the path of light for one particular image, and of course the galaxy is made up of stars, then stars, individual stars within the galaxy can sometimes give a sudden boost. That will happen, and that will brighten things up for a period of of days to hundreds of days. And so, for example, people have seen an individual star in a high redshift galaxy as a result of this special boost. But other than that, time variations are not terribly important. So the kind of analysis which we are doing is not affected in a serious manner.
Okay, so thank you.
Excuse me, sir.
Yes.
So one of our audience asked, is it possible to use gravitational lensing around planets as a mirror, or does that randomize the light way too much?
No, in fact, the bending of light around planets is too little, so one cannot do much. Although I should say that bending of light from background sources by planets gives a very, very tiny boost to the brightness of background objects, and this has been used to discover planets around other stars. Okay, so a planet around another star comes in between us and a background star, and because the planet is moving in its orbit, it will not stay put at the same location. The brightness of the background star gets a boost for a short amount of time, which could be a few days.
Okay, and what about the lensing around stars? Can we use that as a mirror, or does that also?
Not as a mirror, but one can use it as a lens, except that if you try to come up with an optical analog for this lens, it has a very, very funny shape. So you cannot form a sensible image as such. Okay. So if you try to think of it in terms of a convex lens, then that is a very, very poor analog, because over here, the effective curvature of the gravitational lens increases very sharply close to the center. So it's not a very very good. It doesn't have a very good correspondence with the convex lens. It is a very weird shaped lens. You can search for optical analogs of gravitational lenses, and you will see, you will find something interesting.
Okay,
So,
thank you so much, sir.
So does gravitational lensing affect redshift and blue shift?
Gravitational lensing in first order, it does not, because you can think of it as a potential well, and light is entering the potential well and exiting the potential well. It does not lose energy. But if the potential well itself is varying while the light is transiting from there, then it can have an effect, but that effect turns out to be extremely small.
Okay, so thank you.
Yeah, so the first order effect would have been to have a change in spectral line where delta lambda by lambda would be of the order of phi by c square, phi being the gravitational potential. But it's a second order effect, so it is of the order of phi square by c4. And if you do a calculation for pi by c square, even in the major gravitational lens systems that we have, it's of the order of 10 to the minus 5. So you're looking at an effect which is like 10 to the minus 10. And at least presently, it is not observable.
Um,
Are there any other
does
questions?
anyone else have any more questions? Okay, it seems like that is all. Thank you so much, sir, for this amazing and wonderful lecture and for taking time out to give it to us. It was really, really interesting.
I'm glad you enjoyed it. And if there are any further questions, people can get write to me on email, and I'll be happy to respond when I find time.
Yes, sir, sure. I'll share your email with them.
All right. Thank you.
Thank you so much for coming, sir.
Yeah. Good night.
Good night, sir.